Welcome back to section 5 of chapter 5. In this section, we're going to start looking at non-right triangles, which are called oblique triangles. That includes both acute and obtuse. And we're going to be looking at how we can deal with trig and solving them. The first one we're going to look at is the law of sines. In the next section, we'll see the law of cosines. They work together to allow us to solve any kind of triangle. So, our learning targets, we can solve triangle using the law of sines. We can state whether measurements determine 0, 1, or 2 triangles. Solve triangles using the law of sines when 2 triangles are possible. Determine if the law of sines can be used to solve a triangle and solve it if possible. And then solve applications using the law of sines. So it's just a whole bunch of law of sines. This section is fairly targeted and specific. It doesn't have a ton of identities like the last one does, it just has one. So the law of sines. Before we get to the law of sines itself, let's look at how triangles are labeled. Because so far we've been looking at right triangles, which have opposite sides, adjacent sides, and hypotenuses. Non-right triangles do not have those things. So if we have a triangle, does not matter what kind of triangle, every time I draw a triangle it looks like it's a right triangle. It doesn't matter, it does not have to be. We label the triangle by the vertices with capital letters. So a lot of times we'll start out with A, B, and C. And it doesn't really matter which vertex is which. Now the sides are labeled with lowercase letters that match the opposite vertex. So we have vertex A here. So side A is going to be across. Side B is going to be across from angle B. And side C is going to be across from angle C. That way, when we have sides and angles, we know exactly what that's going to be. It does not matter where you start really. Most of the time when you're working on these types of problems, I would recommend drawing a picture, specifically of a triangle, and labeling it. Now, if you draw it so that it kind of looks right, that could be helpful. But if you're more of the theoretical, you can see a 20-degree angle and call it a 115-degree angle and be okay with that, great. But if it looks kind of right, it can help, especially when you're just starting out. So now what does the law of sines say? The law of sines says the ratio of the sine of an angle divided by the opposite side is going to be the same for every single angle. If you look in your book, it shows you why this is true. It breaks it into a right triangle and shows you that that works. But sine of A divided by side A equals the sine of B divided by side B equals the sine of C divided by side C. Now, we don't usually have two equal signs in equations, and when you're using this, you're only going to have one. You're going to pick any two and work with those. We can also take the reciprocals of these, by the way. So also, A divided by sine of angle A is going to equal B divided by sine of angle B is going to equal C divided by sine of angle C. So we can do the reciprocals of each of them. They are the same. It's just if we're looking for a side or an angle, I like putting what I'm looking for in the numerator. It's one less step to deal with, but it does not really make much of a difference. So what can we do with this? We can solve. So to solve a triangle, you need to find all three sides and all three angles. You will already know three pieces of information. So you just have to find the other 3. So if we have triangle ABC given that angle A equals 36, angle B equals 48, and A equals 8. So first step, draw a triangle. This is ABC. So angle A is 36 degrees. Notice these are in degrees. Generally speaking, when we deal with law of sines and law of cosines, we'll be working in degrees as opposed to radians. No real reason for that, other than that's just what we probably will be working with. Angle B is 48 degrees, and side A is 8. So in order to use law of sines, what's very important is that we have an angle and a side opposite it, that we know both of those pieces. So here we know angle A and side A. That will allow us to use the law of sines. So we need to find the other 2 sides and the angle. So the first one I would find is the angle. If we know 2 angles, we don't need the law of sines to find the third angle. We just need subtraction. So angle C is going to be 180 minus 36 minus 48, which is, there's my calculator. Not that I need it for this one, but you will need a calculator for a lot of these though, because we're going to end up with a sine of 36 degrees. That is not something you're going to know in your head. So angle C is 96 degrees. That's one of the pieces. Now we can set up trig. So let's find, we have side B and side C defined. So let's find side B. So I know that B over sine B is going to equal A, which was 8, over sine A, which is 36B B was 48. So B divided by sine 48 equals 8 divided by sine 36. Sine of 48 degrees is just a number. We can multiply by that. So B will equal 8 times sine of 48 degrees over sine of 36 degrees. So first thing you want to make sure of is that your calculator is in degree mode, not radian mode. That's one of the biggest mistakes in doing these problems, is you just have your calculator in the wrong mode. And then we go sine 48 equals that times 8 equals, so we had a 0.74 times 8 is about a 5.9, divide by sine of 36 equals 10.11. So B equals 10.11. 4 or 5, but I mean, we're going to round at some point. And then C is going to be basically the same. Side C will equal sine over angle C, which was 96 degrees, equals, and then A over sine A. So 8 over sine 36. Now we could use B over sine B for that, except that B is 10.1145, blah, blah, blah. Like, we have a rounded decimal. A is 8. That's it. So I would use just what you're given as opposed to a decimal that you ended up rounding. So we'd again multiply by sine of 96. So C equals 8 sine 96 over sine 36. Sine 96 times 8. So sine of 96 was 0.99-ish, times 8 was 7.95, and then divide by sine 36 is 13.535, so 13.54. So check, make sure that if you remember in geometry, the smallest angle will be opposite the smallest side, the biggest angle will be opposite the biggest side, and the middle angle will be opposite the middle side. So we have the smallest angle is A, and that's 8. Then we had B, and that was 10 point something, and C was 13 point something. There we go. Generally speaking, having some sort of a way of writing as opposed to, hey, here's all my work. Like we have the work. Um, when you're doing this on paper, having your answers in a way so you have like A equals, B equals, C equals, A equals, B equals, C equals, can help make sure that you don't forget something. Some of it we were given. We knew that A was 8. We knew that angle A was 36 degrees, angle B was 48 degrees. Then we found C was 96 degrees. Then we found B was 10.11 and C was 13.54. And then you have all of the pieces to your triangle all just neatly packaged. So actually having your answer written out like that is generally it helps things. So that's the basics of law of sine. We have an issue with the law of sines, however, and that is with the postulate from geometry, the congruency postulate that you always wished was there but never was. And that would be the angle side postulate. Sometimes it's called the side angle postulate so that you didn't just giggle. And what this gives us is it gives us an ambiguous case. The reason why this was not a postulate is because just because you know that the angle and then side are congruent does not mean the two triangles are congruent. In fact, you could have two possible triangles. What happens here is, so we know an angle. So we know this angle, and then we know, so we have the angle, we know a side, and then we know another side. And let's say this side length, I'm going to draw it in green, just straight down for the length. Let's say it's that long. Well, that long could go to about here, or it could also go to about there. And that gives us two different triangles. It gives us this triangle where we know the angle, the side, and the side. And it gives us that triangle where we know the angle, the side, and the side. So we get two triangles there, possibly. And that is what's called the ambiguous case. So what has to happen for this to happen? First of all, we need an angle side type of triangle. We only know one angle and two sides. Now, if it's a side angle side, we don't have the information to be able to use a law of sines. We have to use a law of cosines for that. But here we do have the information. So it has to be angle side. The far side, so the one that's named the same as an angle. So let's say this is angle A and side A, and let's call this one up here C, and whichever one down here is going to be B. So this is side B, and then side C is going to be the one on the bottom. So we know angle A, we know side A, and we know side B. Side A, well, angle A has to be acute. In fact, it has to be fairly small. It can't be too big. But angle A definitely has to be less than 90 degrees. And generally speaking, significantly less than 90 degrees. It's usually 30 or even less than that. If side A is too big, we wouldn't be able to have this one. Because if side A was bigger than side B, it's going to end up it would end up hitting out here somewhere, and that's not the triangle with that angle. So side A has to be less than side B. And side A also has to be big enough. It is possible that you would have your angle, your side, and then if side A was too short, it wouldn't be able to connect. And that could be problematic. The nice thing about that is that you don't need to necessarily recognize it beforehand. What would happen when you're doing this is when you're solving, you'd end up with sine of your angle, let's say sine of A, equals, and then your ratio after you've divided and stuff, you'd have like 1.09. And then you do the inverse sine. But sine is always in between -1 and +1. And so when you do this, you're going to get an error. If you get an error, that means that that side length is probably not long enough to reach there. And so it's possible to have 0 triangles from this. Most of the time we get 1 triangle. With the ambiguous case, we have the possibility of getting 2 triangles. So let's take a look at a problem here. So we're going to solve triangle ABC given that angle A is 26.3 degrees, A equals 7, B equals 6. So A is bigger than B, so we don't have to worry about the ambiguous case here, which is fine because we're going to see how we can solve to get our other angles. So first, let's draw a triangle. We have angle A. Let's make this one B. Let's make that one C. So B was 6, A was 7, C is unknown. Angle A was 26.3 degrees. So first thing, we have angle A and side A. So we know we're going to have sine of 26.3 over 7 equals, we can't do C yet because we need to know at least one of the pieces, but we can do B. Sine of B over 6. So we're going to multiply by 6. So we have 6 sine of 26.3 over 7 equals sine B. So we can figure out what this number is. Sine of 26.3 is 0.44 times 6 divided by 7. Gives us about 0.3797. So I'm going to write 0.38 equals sine B. Now, I'm not going to use 0.38. I'm going to use the number in the calculator. And we have to do inverse sine. And that'll give us our B. So the inverse sine of that answer is 22.319. So, well, let's go 1 decimal place, 22.3 degrees. So B equals 22.3 degrees. All right, so we found B. Now, we don't know either piece from C, but we know 2 angles. We can find the third angle. That's just subtraction. So C will be 180 minus the 2 that we know, 26.3 minus 22.3. Gives us 131.4. And then we can find side C. C over sine of 131.4 is going to equal A over sine A. So 7 over sine of 26.3. we'd multiply by the sine of 131.4. So we go sine of 131.4 equals that times 7. So we had a 0.75 times 7 was 5.25 divided by sine of 26.3 is about 11.85. So we have the 3 pieces we had to find in addition to the 3 pieces we already knew. So that's a standard just how to find the angle one. If you only know one angle to begin with, first you have to find the second angle. Third angle's by subtraction. But sometimes we have our angle is 30, A is 6, B is 7, which means if we have a 30-degree angle, and this is 7, 6, could be there, or it could be there. So we could get 2 possible triangles. And so for this, we're just going to find both possibilities. So the first one, let's work with this one. So we have A, B, C. That was 7, that was 6, that's 30. So first thing we need to do is find angle B. So sine of 30 over 6 equals sine of B over 7. We can multiply by 7. Sine of 30 is 1/2 times 7 is 7/2 divided by 6 is 7/12. And then we have to inverse sine. So inverse sine of 7/12 is 35.685, so 35.69 degrees. From there we can find C. For C we just subtract. So 180 minus 30 minus 35.69 is 114.31 degrees. And then we can find side C. Side C, we're just going to go C over sine of 114.31 is going to equal 6 over sine 30. So we can multiply. One over sine 30. Sine of that times 6 divided by sine 30, which is 1/2, so times 2 is 10.9359, so 10.94. So that would be one of our possible triangles. The other possible triangle here is going to be the big one where it comes out this way. So we still have 7, we still have 6, we have C, we have B, we have A, we have little c. A was 30. And so first thing we could find sine of B. So we'd set it up. Sine of 30 over 6 equals sine of b over 7, which is the exact same setup that we had earlier, which is kind of strange, right? Except that we would get it, so the sine, remember, is the y value in the unit circle. It's positive in two different places in that first 180 degrees. So it's positive at the 35.69 degrees that we found, and it's also positive at 180 minus 35.69 degrees. That's how you find that other angle. So B is going to be 144.31. So what's funny here is it's the obtuse one, so my diagrams are just switched. It doesn't really make a difference. This is still how you find both. I just have the drawings on the wrong ones. So B is 144.31, which means C, we go 180 minus that, minus 30, gives us C is 5.69 degrees, which if you look up at this angle, that is a pretty small angle, so that makes sense that C is going to be pretty small. And then we can find side C. C over sine of 5.69 equals A, which was 6 over sine of 30. We can multiply that sine of 5.69 over, and then we can do the calculations. So sine of 5.69 times 6 divided by sine of 30, which would be times 2, is 1.189, so 1.19. And so we have those values or those values. And it could be either of them based on the information that we were given. That's why it's called the ambiguous case. It's one or the other. We can't tell which it is. And that's why that angle side-side was never a postulate that you were able to use. So, some applications. These are just triangles. So, Forest Ranger Chris Johnson at Ranger Station A sights a fire in the direction 32 degrees east of north. Ranger Rick Thorpe at Ranger Station B, 10 miles due east of A, sights the same fire on a line 48 degrees west of north. Find the distance from each ranger station to the fire. First step, draw a picture. Sometimes it'll give you a picture, especially if the description is a little bit tough. So here we have the north, so we have 32 degrees from north, we have 48 degrees from north, and they're 10 miles apart. We need to find A and B. So to find A and B, we need first an angle and a side opposite. We know only one side. We know this side. So we need the angle opposite it. We need to find angle C. Well, how do we find angle C? First, we're going to find angles A and B. If this is 32 degrees, and this is a 90-degree angle, because we have north and we have east, we can just subtract. 90 minus 32 is 58 degrees. And then we can do the same thing over here. 90 minus 48 is 42 degrees. From there, we can find angle C because they add up to 180. So C will be 180 minus those two, is 80 degrees. So angle C is 80 degrees. Now we have information we can set up to find these. So we could find A first. So A divided by the sine of the angle opposite it, 58 degrees, is going to equal side C, 10, over sine of the angle opposite it, 80. So we can multiply by the sine of 58 degrees. So A will be 10 sine 58 degrees over sine 80 degrees. Sine of 58 times 10 divided by sine 80 is 8.611 miles. And we can do the same thing for B. B over sine of the side opposite, or the angle opposite, 42 degrees, equals 10 over sine 80. Multiply the sine 42 over, so B will be 10 sine 42 over sine 80. Sine 42 is 0.67 degrees times 10 divided by sine 80. Gives us 6.795 miles. So that's how far each of them is away. One of them's 8.611 miles away, one of them 6.795 miles away. So using these angles and finding the distance, they could actually then put the place the fire on the map. They would know exactly where it is, even though the distance is too far away to really be able to judge where it is. Knowing the angle and the distance between the two ranger stations, they can triangulate where the fire is. That's where the word comes from, because it's based on the triangle. Last one. A road slopes 10 degrees above the horizontal, and a vertical telephone pole stands beside the road. The angle of elevation of the sun is 62 degrees, and the pole casts a 14.5-foot shadow downhill along the road. Find the height of the telephone pole. So, again, picture's nice. What are we looking at? So, this angle is 10. We know that that is 90. So this angle right here from the actual plane of the road to the pole is going to be 80 degrees, which means this other side here is going to be 100 degrees because it still makes a straight angle. We know that the pole casts a 14.5-foot shadow. So that's going to be AB is going to be 14.5 feet. And we know that since the sun is 62 degrees above the horizon, that would be here, and that would also be here. So we could subtract the 10 degrees from that, from the slope of the road. So this will be a 52-degree angle. Which means we can find this angle with subtraction. So 180 minus 100 minus 52 is going to be 28. So we need to find the height of the pole. We need to find A. So we need the sine. So let's see, A over sine of the angle opposite, so sine of 52 degrees equals, and then we know it's 14.5 feet over sine of the angle opposite, sine of 28 degrees. We can multiply by that sine of 52. Divide by sine of 28 degrees. So we have sine of 52 times 14.5 divided by sine of 28 gives us 24.338. So A is 24.34 feet tall. So the height of the telephone pole is 24.34 feet. Now we don't need to find all the other pieces. In this case, it was just asking us what is the height of the telephone pole. So like that side length B, we don't need to find. So this was law of sines. Lots of uses. It's again used to solve triangles, non-right triangles. Right triangles, the sine of the 90-degree angle is just going to be 1. And so you end up with really the sine equals opposite over hypotenuse. But it's pretty straightforward aside from the ambiguous case. That's the one you have to watch out for. Do they show up a lot? No. Are they going to show up a couple times on your homework? Yeah. Is there going to be probably one on your test? Probably. So it's something that you definitely want to watch out for. But other than that, law of sines is just a ratio. That's all it is. So I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.